we'll go into a little discussion summary session. We'll summarize what was going on for the whole week. So that session hopefully will be done by 12:45, and then we'll all go to lunch, and after the end of the school. After that, you guys are on still together, discuss stuff, just for home. Okay, so with this said, let's now go to the last lecture of Liang Fu.
All right, thanks. So I'd like to thank everybody for staying till the last day. So this is the final lecture. Finally figure out something to say. Again, in the spirit of discussing theoretical applications of topology insulators, I'll describe how topology sort of impacts our current understanding of Anderson transition, basically localization transition in a non-interacting disorder system. And in particular, I'm going to focus on 2 dimensions. So this is based on work done with Charlie Kane a few years back. So let me switch to this. Oops, does it work? Need to maybe close this and open this. All right. Okay. So the problem of localization transition is the following. Suppose we have a system of size L, and we ask if we increase the system size towards the thermodynamic limit, how does the conductance of the system scales with its size? And in high school, we learned about Ohm's law, which says that conductance of a metal goes as a conductivity times the area of the cross section divided by the length. Okay, and so this tells us how the conductance of a classical metal scales with the linear system size, and this is in this limit where we start with a good metal with high conductance at a given length scale. If we further increase the system size, we see that conductance scales with just L to the d-1 power, d-2, where d is a spatial dimension. On the other hand, we also know from theory of Anderson localization that if the system we start with is already insulating state, it will have a localization length, which we call Kc. As we increase the system size, the conductance will become exponentially suppressed. Okay, so this basically gives us how the conductance scales with system size in the opposite limit, in the insulating limit, where the conductance at a given system size is very small to begin with. So it becomes smaller and smaller. So this beta function is basically telling us how the conductance at one length scale changes as you double the system size, so-called beta function in the renormalization group flow. And so once we know how the beta function behaves in these 2 limits, in the large conductance limit, it goes as d-2, which is constant, independent of the conductance, and in the localized regime, the conductance goes as this. So one can just now extrapolate between the 2 limits. Okay, so this leads to this very famous result of the scaling theory of conductance. And the important hypothesis, okay, underlying this scaling theory is that there's basically a single parameter that controls the conductance. It's just if we know the conductance at one system size L, we know how the conductance becomes as we increase system size twice, 3 times, etc., etc. So basically, the conductance at twice the system size only depends on a single parameter, which is the conductance at system size L. Okay, so that's a basic hypothesis behind this scaling theory, and we see that immediately in 2 dimensions something interesting happens. So in 2 dimensions, in the case of a classical metal, the conductance basically becomes independent of system size. Yes, right. So this is what the beta function looks like. You see that it's always negative. So this implies that no matter what a good metal we start with in the thermodynamic limit, it always becomes insulating in 2 dimensions. Okay. So one thing I should mention is that this is a particular This theory, this particular flow diagram, is for a disordered system with non-magnetic impurities, the time reversal invariant disordered system without spin orbit coupling. Okay, and this is indeed the exact picture for this symmetry class. Basically, in 2 dimensions, all states are localized. And further, if we go slightly, starting with a good metal, where we use classical formula for conductance, on top of that, we can include the so-called weak localization corrections. This basically due to quantum interference effect. Sort of electron can go through different trajectories in the presence of disorder, and they interfere with each other. And within this symmetry class of a system with no spin orbit coupling, with time reversal symmetry, the weak localization correction is negative. So it asymptotically approaches the beta function asymptotic approaches 0, but coming from below in the large conductance limit. And in the localized regime, the conductance is strongly negative. So that's why it's reasonable to extrapolate that for all values of G in this symmetry class, the beta function is negative. So the conductance becomes smaller and smaller if you increase the system size, that all states are localized. And however, there's we see that since the 1980s, since the discovery of integer quantum Hall effect, you see that something unexpected happens that doesn't quite fit into what I just described. In the quantum Hall states, and again, since I'm talking only about non-interacting systems in this lecture, we're going to just look at integer quantum Hall effects. In the integer quantum Hall effect, the conductance, the diagonal conductance sigma xx is 0 when we are in the quantum Hall plateau, but the Hall conductance is non-zero and is quantized into an integer multiple of e squared of h. And in the case of lambda levels, this n is just the number of occupied lambda levels. Very simple, but we now know more generally this Hall conductance is related to the Chen number, and it has a topological origin. So, for example, a few years ago, there's this experimental observation of the so-called quantum anomalous Hall state without any external magnetic field, and it all comes from band structure effects. And here the Hall conductance is really measuring this topological quantum number, the Chen number. So, one thing I want to emphasize is that whenever we see any interesting topological insulator, broadly defined topological insulator physics of matter, it immediately implies there's a delocalization on the boundary. Right? That's the defining property of topological insulators. Moreover, the presence of conducting edge states also implies there must be extended states in the bulk. Okay, so this argument was due to Berta hovering, and one way to think about is that as we, for example, in the case of integer quantum Hall effect, as we change the Fermi energy, the system must go through a sequence of phase transitions from quantum Hall states to a trivial states. Okay, because we know that in the trivial phase there are no conducting chiral edge states, and in the quantum Hall states there are these conducting edge states, and these chiral edge states cannot be localized within each edge. So the only way for the edge states to change from being present to being absent is to annihilate each other across the entire bulk. So that necessarily requires that at the transition between different quantum Hall states, there has to be extended states in the bulk. So this says that sure enough that there cannot be states that all the way localized from the bottom of the bands all the way to Fermi energy. There somewhere in the spectrum there has to be extended states, right? So this tells us that the extended states must cross Fermi energy at the quantum Hall plateau transition. So not all states are localized in 2 dimensions in this time reversal breaking symmetry class. Okay, so the one I want to emphasize is that the presence of topological insulators in this symmetry class, namely the presence of the existence of these quantum Hall states, immediately implies that the presence of extended states in the bulk, at least at a certain energy. Okay, not all states are localized in this symmetry class. So then, this immediately says that this single parameter scaling theory cannot be fully correct for this time reversal breaking symmetry class. Okay, and this theory basically it cannot be the full story because it does not distinguish different quantum Hall states. As I said, this theory is based on single parameter scaling. That if you increase the system size, the conductance of the twice system size only depends on the conductance system size L. However, we know that, and in this single parameter scaling theory, there's only one kind of insulating states, right? Just conductance goes to 0. Okay. So, whereas we now know that the different kinds of insulating states that are corresponding to different topological index Chen numbers. Okay. So this single parameter scaling theory does not have the capability of accommodating different insulating states. So it cannot be fully correct. And also, this theory does not give any delocalized states. It will say that all states are localized in 2 dimensions, but we just said that at the quantum Hall transition, the bulk must be delocalized. Okay, there must be delocalized states in the bulk. So, so this basically is a first example where ideas from topology, okay, give us insight about the theory of localization. That there has to be something beyond this single parameter scaling theory, and this problem was fixed, at least theoretically. There's a strong argument for a modified renormalization group flow diagram. Instead of based on a single parameter scaling theory, there are really 2 scaling parameters. One is the longitudinal conductance, just like the case for the time reversal invariant non-spin orbit coupled class. But in addition, in this time reversal breaking symmetry class, the system generally can have a non-zero sigma xy, a non-zero Hall conductance. So now, this is a proposed 2-parameter flow diagram by Pruskin in 1980s. Yes?
So I guess for our to understand the importance of the flow diagram, Pruskin not actually follow.
Yeah.
The flow diagram is just written down as
yeah.
experiment.
Yeah.
But then what does it tell us?
Yeah, that's excellent. Yeah. So actually, many of the details of the flow diagrams are conjecture. But this is a key point I want to emphasize, that even though we cannot solve this field theory, which I'll describe in a minute, I think it's generally believed that this kind of a flow diagram structure is at least qualitatively correct. And my argument for this is that single parameter scaling theory is clearly not enough, as I just described. And here, in the system, there are 2 natural variables to consider, which is Hall conductance and the longitudinal conductance. So it's plausible that there has to be a flow diagram like this. It's instead of thinking in terms of the instead of thinking of these 2 variables as some abstract constants, like abstract quantities in the theory, you can think in terms of just the measurable quantities. If I have a system of a given size, I can measure the conductance, longitudinal, and Hall, and then we can ask, how does these 2 measurable quantities change as we change the system size?
What's the predicted power?
So this actually, this is exactly what I'm talking about now. Okay, so what this flow diagram predicts is the following: that if we start with a system at size L, okay, and then depending on what the sigma xy, the Bayer value of sigma xy at the system size L is, and then as you increase the system size or as you go to lower temperature, you end up at different fixed points. So generically, generically, if you start with sigma xy, let's say less than 1/2, you flow to 0. And if you start with sigma xy greater than 1/2 e squared of h, you flow to this e squared of h. Okay. Now that you can think of this as one consequence of this flow diagram. Yeah. Yes.
Is there an argument that the saddle point has to be at half and cannot be to the left or to the?
So you can use particle Hall symmetry, for example. Yeah. If you interchange, field and empty states within the lowest Reynolds level. It changes the Hall conductance by this. And yeah, so one of the consequences of this flow diagram is it says that, again, this is more of a just based on physical arguments, but it also sort of matches with mathematics, as I'll describe later. Anyway, so the stable fixed points corresponds to where the sigma xx vanishes, but sigma xy become quantized into integer multiple of a square of h. So this is this describes the quantum Hall plateaus, describes the quantum Hall effect. And it also says, when the Hall conductance is 1/2 e square of h, you have unstable fixed point at the quantum Hall plateau transition at the critical point. So slightly perturbing sigma xy across this line, it goes to different quantum Hall states. And at this critical point, you see that sigma xx flows to a universal value. Again, this part of the flow diagram is all based on essentially our physical understanding instead of actual calculation. Okay, there's no controlled calculation done in this regime. But we know that the unstable fixed point has to be there because this is right at the quantum Hall plateau transition points, and at this critical point, there has to be extended states in the bulk, so the conductance has to be non-zero. Okay, yeah. All right, so then, so this is the situation with this the time reversal breaking symmetry class in 2 dimensions. But now, starting from more than 10 years ago, we now also know that in the time reversal invariant class with spin-orbit coupling, there are also 2 kinds of insulating states. There is this trivial insulator, then there are also topological insulator, quantum spin Hall states. And so this is the symplectic class, the so-called symplectic class, time reversal invariant spin-orbit couple system. And again, the topological insulator in 2 dimensions has conducting edge states that are helical, meaning that spin up and spin down states going in opposite directions. And time reversal symmetry guarantees that a non-magnetic impurity cannot backscatter, because backscattering requires a spin flip, which is impossible. Or a more rigorous way of saying this is that the counter-propagating states with opposite momentum and opposite spin, they form a Kramer doublet. The Kramer's pair and the backscattering between Kramer's pair is forbidden when time reversal symmetry is present. It has to do with the fact that t² is -1 for spin 1/2 particles. So so that's why we theoretically expected that the conductance at each edge at 0 temperature is e² of h, independent of system size. And experimentally, some approximate quantization was seen from the early days in mercury telluride, cadmium telluride quantum wells. Although the quantization is actually poor, it's not ideal, far from ideal, and actually still it's not quite understood what is the origin for this. Yes. Yes. Yeah.
So, what about the C2 invariant?
That's exactly what I'm going to talk about in this lecture. That's the content of this lecture. Yes.
So what I'm saying is, when it was known that was a
No. That's exactly no. Yeah. So instead, that's exactly the point of this lecture, that the insight from topological insulators will help us fix the theory of Anderson transition in the simplex class. I think I know the paper you are referring to. I'm trying to remember. That. Yeah, we can chat about it. I don't know if he's talking about the simplex class. I don't remember now. Back then, when we wrote this paper, we looked into that paper. So okay, I can. Yeah, we can chat about that. Yeah. But the theory that I'm going to present is different, totally different from whatever is in his paper. That I'm very sure. Yeah. Okay. More recently, there's also this second material platform for at least some evidence for quantum spin Hall states in indium arsenide and gallium antimony, where the conductance seems to be better. This talk was given in 2012, and I think since then there's also some debate about this material class. So I won't get into that. Okay, so again, then we have the same argument again, right? So I'm almost like repeating myself because you see that the spirit is really very general. Because there exists two classes that are of insulators in the simplet class in 2 dimensions that are topologically distinct, it immediately implies that there has to be extended states at Fermi energy at the topological phase transition, right? Because there's no way of changing the system from having topologically protected edge state which conducts to another state which does not have conducting edge states at the boundary. And conducting edge states cannot vanish by itself. It has to connect with its partner at the other edge, and this pair annihilation can only occur when the bulk has extended states. If the bulk states remain localized, the two edges don't talk to each other, right? And indeed, numerically, shortly after the K-Mali work, there's a numerical calculation of the K-Mali model in the presence of disorder, and you find that indeed the topological insulator regime is separate from a trivial Anderson insulator regime by a finite region of metallic states. So this is different from the quantum Hall transition. In the quantum Hall transition, the transition occurs in one step. At the quantum Hall transition, the system is critical. But here, there are extended metallic states separating the topological insulator phase and the trivial phase. So yeah, this is Leo's question. That before K-Mali, this is a proposed single parameter scaling theory based just on the conductance. Again, what led to this scaling theory is that if we start with good metal, one can look at the so-called weak localization corrections. And in this time-Russell invariant class, it turned out that the interference of electrons passes. They interfere constructively, so they enhance the conductance instead of decrease it. So that's why once quantum effects taken into account, the beta function is actually positive. This is saying that if we are on this side, then if we start with a metal at the system size L, as we double the system size, the conductance becomes even better. So the conductance increases with system size. Okay, very counterintuitive, but this is correct. That as you increase system size, the conductance increases. So we get a metal. On the other hand, with strong disorder, there has to be localized regime. So there we get an insulator. So there was then it was extrapolated that there has to be a metal insulator transition at a certain critical conductance, right? But we now again see that this flow diagram contradicts with what we now know from topology. The presence of a topological insulator says this flow diagram cannot be the full story because in this theory there's only one kind of insulating states. Right? It's just one kind of insulating states. It does not distinguish conventional and topological insulator in 2 dimensions. So yeah, again, you see that the idea of topology can give us a lot of powerful constraint on what a theory could be. So this has been a question for quite a while. That we know in the quantum Hall case, after the discovery of integral quantum Hall effect, the single parameters scaling theory was disproven, and this is a proposed flow diagram in terms of 2 parameters. Okay, but what about the corresponding phase diagram for a 2-dimensional symplectic class? Okay, after we know the presence of topological insulators, this is a problem we thought a lot about back in the early days, but only and the key challenge here is the following. In this quantum Hall class, there are 2 natural quantities, the longitudinal conductance and Hall conductance, and these are the 2 parameters. Basically, they naturally appear in the theory of the localization for this class in terms of nonlinear sigma model that I'm going to describe. But in the topological insulator class, we don't quite know what is the counterpart of sigma xy. Right? What is the second scaling variable? Right? So that has been the challenge. So now, what I'm going to describe is now we know at least in theory what the second variable is. And again, this is just to give you the sort of the criterion for whatever this theory is. It has to have certain features. What we are looking for would be a quantity that is universally defined, which can distinguish the trivial and topological insulators within the field theory, within whatever theory that you like. And in particular, I'm going to focus on the so-called nonlinear sigma model description of the Anderson transition. So we need a quantity in this theory that can distinguish the two topologically distinct phases. So that with that extra quantity, we can make a two-parameter flow diagram of sigma xx, this sigma xx, and this quantity I call nu. And this quantity nu has to be defined basically for a given system size, and we should look at how this quantity scales with system size. Right? So let me first review very quickly what the so-called replica field theory is for disordered systems, non-interacting systems in the presence of static disorder. So basically, in the statistical mechanical system, we are interested in free energy, which is the log of the partition function, and we want to do disorder average of the free energy, but that's difficult. It's much easier to just think about the powers, the disorder average of the powers of Z. But then there's this trick that we can consider n copies of the system, and as a whole system is a partition function of Z to the n, do disorder average, and then take this particular limit where n goes to 0. That gives us log of Z. And the disorder average of the partition function to the nth power can be written by like this. This is a clean Hamiltonian H naught. E is Fermi energy, and delta and so let's see. So what I'm doing here is I'm averaging over disorder configurations, and right. So we are averaging over disorder configurations, and by doing that, we obtain an effective 4 fermion interaction. So I'm not going into the details, but the idea is that we start with a problem of n copies of the fermions with n flavors interacting with disorder. We integrate out disorder configurations. We perform the disorder average, and we generate a 4 fermion interaction. Okay, and then this 4 fermion interaction can be Hubbard-Strinovich transformed using a field, so-called a Q, and this Q lives in the space of flavors. Right, so Q is a matrix in the flavor space. Okay, so with this, basically, we turn a non-interacting problem in the presence of disorder to a interacting problem without disorder. Okay, that's the general spirit. And the subtlety here is that at the end of the day, we need to take the limit and go to 0. So that's always the difficult part. But we will sweep that under the rug at the end of the day. All right. So for now, basically the problem of metal insulator transition through this technique, this problem of metal insulator transition is mapped to a problem of interacting fermions, and moreover, in this interacting fermion system, there are two phases. In one phase, the order parameter Q in replica space, the flavor space is also called replica space. In replica space is the order parameter is 0. That describes basically a disorder phase. Or you can think that this order parameter Q in the replica space is strongly fluctuating. It does not have any long-range order. So basically, an insulating state maps to a disorder state in this interacting problem, and the metallic states corresponds to the order states in this problem. Okay? Yeah.
So the gap state is the disorder?
The gap state is disorder states. Yes, correct. It has exponential correlation lengths. Yeah. Yes, absolutely. And in the order states, what roughly is happening is that in the order state, there are many goldstone mode, some analogs of goldstone mode. That's why it corresponds to a metal. Now, one feature I want to point out is that because we are in 2 dimensions, the effect of fluctuations are very important. And for example, we can basically freeze. The conventional treatment is that we freeze the magnitude of the order parameter. So in the Q would have a definite amplitude, but then the Q can point in many different directions in replica space, and these different directions are related to each other by rotation, okay, in replica space. So these are this 1 minus 1 you can think is a fixed order parameter in a particular direction, but the most general order parameter can be obtained from a particular direction by rotation. This is O, okay? And so that's why the fluctuations around the so-called mean field saddle points are described by just the fluctuations in the transverse direction, in the directions of the order parameter in terms of this rotation matrix. Oops. What's happening? I still have it here. Huh? Oh, back. Okay, right. Yeah. So no, without going into details, basically that there's a stiffness term that describes the sort of kinetic energy associated with, or with the stiffness. There's a stiffness term associated with the stiffness of the order parameter fluctuations, and this stiffness term 1 over T is basically related to the conductivity. So let's see, if we have high conductivity, it means that the T is very small, so it gives you a high energy penalty for deforming the order parameter. So that this tends to give you an order phase, right? So basically, the renormalization group flow for this coupling constant or the stiffness T gives rise to the scaling of the conductivity. Now, what exactly this order parameter is depends on the symmetry class. In the orthogonal class, this order parameter O, this order parameter Q lives in the so-called symplectic manifold. In the unitary symplectic class, the manifold of the order parameters in this complex Grassmannian manifold, and in the time-reversal invariant class, this order parameter Q is in the real Grassmannian manifold. Okay. What's interesting is that these magnitudes sometimes have non-trivial topology. So you heard yesterday from Xiaogang, the pi 1, the first homotopy group, that basically tells you if you have a loop in that manifold, whether this loop can always be smoothly deformed into a point, whether loops are always contractible or not. If the first homotopy group is non-zero, it says that within that manifold, there are certain closed passes that cannot be contracted to a single point. And there are also generalizations. There are higher homotopy groups. For example, the pi 2. Pi 2 basically says that if you have a manifold, and if you look at a sphere, a two-dimensional sphere within that manifold, whether the sphere can always be contracted to a point or not. So when pi 2 is non-zero, the contraction is not always possible. They are basically fundamentally inequivalent spheres that can be embedded within that manifold. So the topology of the manifold is characterized by the homotopy group, and when these topological index are non-zero, it allows some additional topological terms to the nonlinear sigma model. Okay, that can be added to the nonlinear sigma model. Yes?
Now you're working in two spatial dimensions.
Two spatial dimensions. There's no time. There's no time. Yeah, when I'm working on two spatial dimensions that describe the bulk. From this point on, it's all about the bulk, because the edge is well understood, right? Yeah. The edge is always metallic. In the chiral edge states, for quantum Hall states, edge states simply cannot backscatter. And in the helical case, the edge states are counter-propagating states, but time rules of forbids backscattering. So the edge is fairly simple.
The reason I ask is because and you were telling us something from the localization point of view, but in that case, they were working on the edge.
Yeah, exactly. Here, that's a key difference. That's a key difference. Yeah. And now I'm going to connect edge and bulk in this field theory in a minute. Yeah. All right. So let's again first look at the unitary class, right? The time reversal breaking class. In this class, the order parameter lives in the complex Krafft-Spanian, and the only possible topological term is associated with the second homotopy group. So that's why we can add a term like this. Basically, when the order parameter forms some non-trivial winding in the Q as a function of x and y. Okay, in real space, when the order parameter basically what this is like it's a mapping. The order parameter Q in real space with xy coordinates has certain configuration. This configuration basically gives rise to a manifold in the order parameter space Q, right? So when this for this particular manifold, and we can actually look at a simple example. So when n is equal to 1, this U2 divided by U1 cross U1 is just a sphere. So now we have a mapping from real space to an order parameter space, which is a sphere. So we can have a skyrmion configuration, right? The skyrmion configuration have a non-trivial, basically this pi 2, where the index associated with the skyrmion is integer, is 1, is non-zero. Where in the other case, if I have, for example, all the if I think of this order parameter living on a sphere as like a spin, if all the spins are pointing up, then the corresponding topological index for that particular configuration is 0. Okay, when you have a skyrmion, you have a non-trivial topological index 1. Yeah. So then one can add a term to the partition function, which is some constant times. Basically, there's a phase factor. One can add a phase factor associated with this particular with this topological index for each configuration, right? So different configurations have different stiffness terms. The stiffness term is non-universal. It depends on details, but every configuration also has a topological index, and the value of the topological index enters into the partition function by this term, which is the topological term. It's a term that's allowed to be added, right? And actually, you may have heard in this school, a very similar case arises if we want to describe, for example, spin 1/2 chain, right? So now with this in this Pruskin theory, there are really two coefficients. One is the stiffness term, T, but then there's another stiffness term, which is the so-called theta term, that it is a coefficient of the topological term. So these two terms can be exactly identified. Can be, one can argue that these two quantities, T and theta, are basically the sigma xx and sigma xy, the longitudinal Hall connectance. For example, if we have a time reversal invariant system, we know sigma xy has to be 0. Right? That's where the theta term has to be 0. So theta equals integer corresponding to the quantum Hall plateaus, and when theta is half integer, corresponding to the plateau transitions. So, and within this theory, there's a very clearly symmetry between theta and 2 pi minus theta. Okay, that you can check easily. So this forces the transition to occur exactly at theta equal to pi. Okay. So this is a case for the unitary class. What about the simplex class? Okay. So remind you that the simplex class has two topological indices, pi 1 and pi 2. So then the first thought would be, just following the spirit of the unitary class. There is the second homotopy group is non-trivial. It has a Z2 index. So perhaps the topological term associated with that will describe a theory of Anderson transition in simplex class in 2 dimensions. But that turns out not to be the case. So instead, the second homotopy class, the second homotopy map, the Z2, what it actually describes. So first, let me mention that if you look at this term, because this second homotopy class is Z2, okay, it immediately says I cannot write down a term like this with arbitrary coefficient, okay, because you have to satisfy addition rules that if I take two configurations and if in semi-infinite space I have one configuration and another semi-infinite space I have another configuration, so that in each region the index for the configuration is 1, But then for the entire system, the topological invariant is actually 0, because for the Z2 class, 1 plus 1 is 0, right? So that's why if the topological index is a Z2 type, it forces that the coefficient in front can only be 0 or pi, okay? It cannot be arbitrary. For any length scale, it cannot be arbitrary. So that's why this being Z2, this pi 2 sort of topological term cannot describe a flow diagram like this in the unitary class, right? In the unitary class, as you see, the bare value of the theta coefficient can be arbitrary, and renormalization group flow takes you to quantized values, either integer in the quantum Hall states or half integer at the transition. Whereas in this case, in the simpler case, this second homotopy group gives a Z2 index. It cannot flow. Okay, it's either 0 or pi. Okay, so what this Z2 index actually describes? Yes. Yeah. Yeah. Absolutely. So there are two theories. In one theory, the topological term has a coefficient which is 0. In the second theory, the topological term has a coefficient which is pi. What I'm saying that if you take any theory, then the coefficient is fixed. It cannot flow. It's either 0 or pi at all length scales. No, it cannot. That's my point. That it's not allowed. Yeah. The argument is the following. The argument is that that if I look at the order parameter spatially, right? So I can suppose this is my entire space. I can make an order parameter which has topological index n equal 1 in this region, right? And then make an identical copy in this other region. The two regions are far apart, right? And locally, I can make the order parameter 1s in this region, and locally, I can make the order parameter 1s in this region. So they are spatially separated, right? So then we expect the partition function has to be additive because the two regions are spatially separated. Okay, but then if you look at the topological term, this region, for example, it corresponds to, it gives you contributions e to the I theta times 1. And this region gives us e to the I theta times 1. But then it must be equal to e to the I theta times 0, right? Because this total index for this entire configuration, right? Because topological index, you can define for the entire system. For this entire system, this 1 plus 1 is 0. This topological index is 0. Okay, so this then immediately implies that theta can only be 0 or pi. Right? Yeah. Okay, so now so what are these two? So theta equals 0 and pi are the only two allowed possibilities. What are they actually describing? Now, this was actually figured out. I don't have the references here. This is actually by Shinsei Ru and collaborators, as well as I think Andrea Luswig. Okay. Anyway, so it turns out that for any two-dimensional system, for a strictly two-dimensional system in the simpler class, this theta value is always 0. Okay. And for the surface state of a three-dimensional topological insulator, there's an anomaly, and those single Dirac fermion surface states in the simpler class are described by a theory where the theta is actually pi. Okay, so the theta equals 0. In one case, it describes a 2D system, and in the other case, it describes the surface of a 3D topological insulator.
So you're saying for true 2D system, whether it's trivial or
it's not. It has nothing to do with pi 2. Exactly, that's my point. Okay, and this lecture is going to focus just on 2D system. Okay, so for 2D system, okay, even though there in principle allows a topological term with coefficient 0 or pi, that doesn't play a role. The theta is 0 for all two-dimensional systems in the simpler class. So this led to the only one possibility left. The first homotopy group is actually non-trivial. It's Z2. That's exactly what has always been the belief in the community. Yes, it has long been believed that pi1 is irrelevant because in this theory, the order parameter has a fixed magnitude, right? Sort of the magnitude is fixed. So pi1 corresponds to topological defects. Its role was completely unrecognized. Okay, so but that's my theory. That's our theory. That work with Charlie Kane in 2012. That pi1 is actually crucial. Okay, the first homotopy group is crucial. So the first homotopy group in the two-dimensional system basically corresponds to topological defects. If I have a defect, the order parameter would wind around that defect in a non-trivial way. The order parameter field has non-trivial winding. Okay, if you stay away from the center of that defect, and that corresponds to a non-trivial element in the first homotopy group, and this is Z2. Okay. So what this says basically is that now in this theory, it actually, if we soften the constraint, right? Because after all, this order parameter, what's the reason that the order parameter has to have fixed magnitude? Now we know like things like XY transition, right? And in fact, for this theory, when n is equal to 1, O2 divided by O1 cross O1 is essentially a circle. Okay, it's a circle. So in the limit where n is equal to 1, it's an XY model. Okay. So this allows vortex configurations. If we allow for vortex configurations, then pi1 become pi1 being non-zero implies that if the order parameter of the order parameter can be softened, it allows topological defects, and these are we can call it vortices. But the important difference that here for all the n greater than 1, this is a Z2 type of vortex. Two vortices can pair annihilate with each other. In a special limit, when n is equal to 1, this becomes instead of Z2, it becomes Z. So if I have a vortex with an odd number of a winding number, that is smoothly connected to the Z2 vortex when you generalize n to greater than 1. Okay. So in other words, in general, for general n, the vortex is Z2 type. In a special limit, when we have just n equal 1, the vortex is enlarged to have a Z class. Okay, so vortices can pair annihilate. So this then says when we sum over all order parameter configurations, that there can be contributions from vortices. Now, vortices comes with a Fugacity, and the Fugacity is a continuously tunable parameter, right? Okay. So unlike the coefficients of a Z2 type of a topological term associated with pi2, here when we talk about pi1, we have defects. So the defects contribute to the partition function. Basically, there's an energy cost associated with every defect, right? So this is called and the basically the chemical potential for these defects are the so-called vortex Fugacity. Now, because this the defects is of Z2 type, two defects can pair annihilate. This says that the vortex Fugacity can be actually either plus or minus 1. Okay, so there's this vortex Fugacity that can take real values, but it can be either positive or negative. And I'm going to argue that that the sign of the vortex Fugacity distinguishes two different phases. When the vortex Fugacity is positive, we have a conventional insulator. When the vortex Fugacity is negative, we have a 2D topological insulator. Okay, yes?
I'm sorry, from this topological term, where can I see it as
the sign? The sign is either positive or negative. So I'm going to argue for you. I haven't finished. This is a statement. Yeah, yeah. Okay, so we can do an explicit calculation. Okay, so how do I extract the sign of the vortex Fugacity? Well, let's look at how this whole nonlinear sigma model was derived in the first place. We have a bare Hamiltonian, and this bare Hamiltonian can either be for a trivial insulator or for a topological insulator, right? E is Fermi energy, and the order parameter is a matrix in the replica space. It couples to the fermion bilinears. So we're now going to take a Hamiltonian for the clean Hamiltonian, which is described by a 4-component Dirac fermion in 2 dimensions. Okay, and the Dirac fermion has a mass. So when we change the sign of the mass term, the 2-dimensional system in the clean limit goes through a transition from a trivial insulator to a topological insulator. So the sign of the Dirac mass changes the Z2 topological class. So what we're doing now is just integrate out the fermions, not for a uniform order parameter, but for a vortex configuration, right? When the order parameter has a vortex configuration, we integrate out the fermions to obtain the contribution of that, to obtain the contribution for that vortex configuration. And again, I'm not going into details, but it turned out that in the presence of this general order parameter winding, this particular problem is basically an antisymmetric matrix. You can define the Pfaffian of the antisymmetric matrix. And when the sign of the M changes, basically the partition function basically is related to the Pfaffian of this kernel here, and that is given by the product of eigenvalues. You are only going to sum over. In this problem, basically the eigenvalues of this kernel comes in plus minus pairs, and the partition function is basically the square root of the determinant is given by the product of half of the eigenvalues. Let's say just take half of them, right? Okay. But when you form a vortex configuration, and then you look at how the entire eigenvalue spectrum evolves as a function of the Dirac mass, there is guaranteed to be a level crossing. So we explicitly show this, and this level crossing it tells us that the Pfaffian changes sign across this transition. Okay, and when this sign, because if you take the product of just half of the eigenvalues, as you follow this eigenvalue across this transition and go through 0, it changes from negative to positive. So that's why the product of the eigenvalues change sign. Okay? So the vortex fugacity indeed changes sign together with M. Okay. Yeah, but actually Pfaffian is half of that. Pfaffian just half of the eigenvalues. So actually, this is an important technical point that what we are doing is slightly different. Because of this, in the simpler class, we can actually just sort of what we call n is what in the literature called n over 2. You can think of that way. So the general contribution to the partition function, if you take n, that is a determinant, but we can do even better. We can just look at half of the eigenvalue. You can just look at n over 2. Sort of the replica index can be half integer. You can think of that way. And in this case, it's Pfaffian. Okay. But independent of whether you talk about determinant or Pfaffian, this spectral flow is real. Okay, it's real. And if we work with half of the number of replicas, we can always work with the Pfaffian. And in the Pfaffian, when you have a vortex configuration, the fugacity change sign. Yeah. Okay. So this immediately says that the sign of the vortex fugacity is tied to the topology of the system, whether it's trivial or non-trivial. Yes? That's for the clean system. For a clean system, yeah. Which H0? This is the same H0. Yeah, exactly. Exactly. So we are literally just sticking this into this, and we choose a vortex configuration for Q. Which vortex configuration doesn't matter. It doesn't matter. The spectral flow holds for all vortex configurations. This spectral flow as a function of M.
What's the claim? So you take Q that has that vortex configuration in the first round.
Yes, and you look at the kernel of this whole thing here. This whole thing you can think of as a matrix, right? It's a matrix in the spin and orbital space, but also it's spatial dependent. It's also in replica space, and it's also spatial dependent, right? It's like this kernel has a spectrum, and once I integrate our fermions in the presence of this kernel, I get basically the product of the half of the eigenvalues for that kernel. So that's why we look at the spectrum of that kernel, and the spectrum of that kernel will show a level crossing across 0 as a function of M. So I'm not proving this, but this is the case. Yeah, it's true.
I guess what I'm asking is, this is what I'm by hand rather than way. Yeah.
Yeah. So here I'm deriving microscopically the vortex fugacity. Exactly. Yeah. Thank you for clarify this. So I'm literally showing that if I integrate the fermions for a vortex configuration, I get a contribution to the partition function, and that contribution can come with two signs, either plus or minus, depending on whether what the sign of M is. That's exactly the point. Yes, thanks. Okay, so so this basically shows that microscopically, although I'm not proving this, this is we really derive this microscopically. Basically this problem can be mapped to problem of like Majorana fermion. But this is exactly the same problem as sort of in the quantum spin Hall this is exactly the same problem as like the vortex of a topological insulator, essentially. It's exactly the same problem. Yeah. All right. So okay. So now we can further look at how the sign of the vortex relates to. We can also look at the partition function in the open system. Okay. Instead of thinking about closed system, we can think about open system. So let's imagine the following setup: that spatially in this island we have a topological insulator, and outside we have a trivial insulator. And then in this system, the entire system can be closed, but it has two regions: the topological region and trivial region. Then the number of vortices in the topological region can be both even or odd, because vortices can be dragged from inside to outside. Right? So imagine that I have a disordered system where in this island it's topological region, outside is non-topological region. So I can study the partition function for this combined system, right? And in this combined system, the number of vortices in the topological insulator island can be odd. So in that case, you see that the partition function for this entire system really depends on the partition function will be literally different, right? Every time I have an odd number of vortices, it leads to this sum, which is an opposite sign than for the case where we have an even number of vortices. Okay, so basically the number parity of vortices, whether I have even odd number of vortices, and actually, yeah, sorry, I'm not saying it right. Let me first say this following thing. So when there's an odd number of vortices, okay, inside the topological insulator region, it implies that the order parameter along the boundary also winds, right? Because it's like if I have a vortex here, I can infer the presence of this vortex by just looking at the boundary. There's a winding number. So when there's odd number of vortices inside the topological insulator region, it immediately implies there's non-trivial winding at the edge. Okay, and then what this partition function effectively does is it gives you a -1 sign whenever the order parameter has a non-trivial winding on the edge. Okay, so this actually is the vortex fugacity basically is also sort of the sign of the vortex fugacity basically depends on the number of vortices inside. It also is equivalent to the homotopy class of the order parameter on the boundary. Okay, so I'm emphasizing this because if you look at the order parameter on the boundary, it doesn't vanish there. It's everywhere has a fixed magnitude, right? So what this basically says is that in this configuration where there's an interface between topological and the trivial insulator regions, the configurations of the order parameter with odd number of vortices in the island are weighted by -1, but that is equivalent to the Z2 topological term for the boundary. Okay, and this is what previously Andreas Ludwig they were talking about. That if I only look at the boundary, there's a natural pi1. Okay, if I look at one-dimensional system alone, the first homotopy group being Z2 implies there are two classes of theories. In one case, the topological coefficient is theta equals 0. The other case is theta equal pi. And he identified theta equal pi as describing the edge state of a topological insulator. What I'm saying here is that if you look at the bulk of a 2D insulator, okay, there's also contribution from pi1, and this is the vortex configuration. But in this geometry, when I have a topological regions interface with a trivial region, the number of vortices in the bulk is the contribution from that is equal to the contribution from the boundary. Okay, these two are there's exact bulk boundary correspondence. Yes. No, the details also matter, but the important thing is if I compare two theories where the if I have an entire region which is topological, which is trivial, right? If I have an entire region which is trivial, you still have vortices, and they also contribute, but they all contribute with the same sign. And in that case, you have localized states, right? But when you have this configuration, vortex can contribute with negative sign. The plus minus terms can cancel, and that leads to delocalization on the boundary.
So just by Z2, you mean actually inside the exponent, inside that form.
Exactly, because only inside this region, the vortex Fugacity is negative,
yeah.
right? There are many vortex contributions outside as well, but those all add up together. The only negative contribution, which is important, actually come from when there's odd number of vortices inside.
So I guess the Z2 does not correspond to the even or odd number of vortices, but comes from whether you have -1 the end.
Whether you have
That's the Z2.
well, let me actually I think maybe the next slide will clarify this. Okay, all right. Let me continue the next slide. Yeah.
We also in that case, that partition function is over all
Everywhere, yeah.
but then you say
Exactly. So if I want to look for those which give you negative contribution, I only need to look at the boundary. Exactly. And that's where you see that boundary is special, because boundary is helical, and boundary have this term which makes the system everywhere can be localized, but that boundary cannot. Okay. So now what about a closed system? If I have a closed system, the number of vortices inside is always even. Okay, so it says this theory is capable of keeping track of two types of topological states, the vortex at plus sign and minus sign. But if I have a closed system, that partition function is always the same, right? Because when the vortex factor is negative, but you always have an even number of vortices, the contribution is still plus. Okay, so this immediately implies the symmetry that the transition. Maybe I'm jumping a little bit. Yeah, the transition from a metallic phase to the insulator states and to the topological states. The exponents are completely identical. All the behavior are identical because the partition function, they only differ by a sign of a vortex Fugacity. And in a closed system, the number of vortices is always even. Anyway, to see the real effects of physically, to see the physical effect of the vortex Fugacity, you need a boundary. Okay, that's yes.
What's the left? I can choose that path C to be inside the eye.
Oh, then what happens?
I still have that say 3 vortices that are
Excellent question. So suppose this is TI region, this is outside in the trivial region. Suppose we choose this path, right?
including let's say odd number of vortices.
Vortices. But then you see the entire. Suppose the extra vortex is here. As I said, in the TI region, this is TI region, right? The vortex comes with minus sign Fugacity. So if I have this configuration, the total contribution to the partition function is still positive, because there are 4 vortices inside the TI region. Right? So these two are exactly tied to each other. The fact that the vortex Fugacity is only negative in the TI region implies that only when there's odd number of vortices in the TI region, it gives you a negative contribution to the partition function. And in that case, there's also this winding at the edge. Yeah, I think I'm not explaining it very well, but hopefully. So you see, this is exactly the bulk boundary correspondence. That when there's a negative contribution to the partition function for this setup, there has to be a non-trivial winding on the edge. And that also implies there's odd number of vortices in that TI region. The two are exactly equivalent. So the previous theory only focused on the edge, so it's not capable of describing the bulk. But the bulk theory, when the vortex Fugacity is put in, it describes both the bulk and describes the boundary. Okay. Yeah. Okay. So now the question is, with the vortex Fugacity, what about the RG phase diagram? As I said, Pruskind theory is basically a sketch. There are 2 parameters that are incorporated in the theory, coupling constant and the theta term, but the RG flow is basically the conjecture. Here it turned out I'm going to describe sort of one particular method where we can make a little bit of analytical progress. It involves analytic continuation. So So we treat the number of replicas again as a continuous parameter. Okay, so n is supposed to be integer, and we're supposed to take the limit n go to 0 in the end of the day. So let's just treat n as continuous and see what happens. And you can see that n equal 1 is very special because for n above 1, this is just the RG flow for the coupling constant without taking effect of the vortex fugacity. When n is above 1, basically the system flows to insulating states. When n is less than 1, it flows to metallic states. In the limit of small t, right? Because calculation can be sort of controlled when t is small, when we are basically in the order phase, right? But when n is greater than 1, basically this is is analogous to like order parameter being a sphere in 2 dimensions. We know that in that case, when the order parameter is S2, it always flows to the gapped phase, right? Gapped phase is the insulating phase. Whereas when n is less than 1, it flows to weak coupling. Basically, the system becomes metallic states. So that's what the previous theory is saying, that if I just look at the coupling constant itself, in the limit when n go to 0, the weak coupling, the small t limit becomes metal. Okay. Right at n equal 1, the system is basically is a XY model, and in that case, the beta function is 0 to all orders. So this is the RG flow. What is it like? For n greater than 1, t flows. You flow to small. This is g. This is g, which is inverse t. You flow to this t go to infinity, get into a localized. Basically, t blows up. T blows up, and you get a gapped phase. When n is smaller than 1, you flow to the metallic, to the order phase. When n is exactly 0, you are in the XY model. But we now know that. But we also know that XY model has vortices, right? So these are exactly the vortices I just described. And when we include vortex contributions in this 2-parameter flow diagram, there's the Costalles-Taulas phase diagram, this transition at special value of t. So, yeah. Rahul, yeah. The sign of vortex doesn't matter. The sign of vortex doesn't matter. In other words, exactly. Yeah. Oh, here, the vortex fugacity is not 1. It's not 1 at all. The vortex fugacity is a continuous variable. It depends on the system, how much disorder you put in, for example. So the sign of vortex fugacity corresponds to the 2 class, trivial insulator or topological insulator. But the absolute value of the vortex fugacity is important for understanding the symplectic transition. Yeah, vortex fugacity has to be has to be plus or minus sign. Has to have either positive or negative. So basically, if what I'm saying basically that, basically it's this, right? So if
fugacity of nothing is 0.
So basically,
1, I guess.
If you have 2 vortices, right? The contribution can be, this is negative, but let me define V to be positive, right? And this gives me V squared. So that's consistent with the fact that having these 2 vortices, the topological term, topological configuration, total topological charge, if you wish, is still positive, right? Because
if I parallel, I get
so here I mean unbounded vortices, right? Is that what the question is? So if I have unbounded vortices, like in KT transition,
right,
vortex have a contribution to the partition function. The only difference here is that in the KT transition, the vortex fugacity is always positive because it's e to the minus beta mu, right? It's
KT, I can't parallelate vortices and anti-vortices.
In other words, let me give another example. Like if you, for example, think about a theory where a vortices only come in Z2 types, I mean they also contribute to the partition function. Yeah, even though if you have even number, even the total system can have just even number of vortices, which is equivalent to having no vortices. But there are still Z2 defects can still play a role in the order disorder transition. Yeah. Yeah. That's an excellent question. So I'm actually what I'm doing here is the following. This is exactly what I'm going to describe. So I'm when n equals 1, the vortices are basically the vortices in the XY model. So there's a lot that's known in that case. So I'm going to now analytically continue, right? Because n is supposed to be 0. What I'm going to do is 1 minus epsilon expansion. When n equal 1, I have the KT transition, and I'm treating epsilon as a small parameter.
Is it known that the theory with the vortices in the
The XY model only have integer vortices, right? The vortices have got vortices are enlarged, yeah. But that's the best we can do, that because when n is not equal to 1, we can't solve that theory. Let me put it this way, yeah. But n equal 1, and you see n1 equal 1 is special. N equal 1 is exactly what because yeah, I'm not saying this very well, but n equal 1 is borderline. So the disorder system is closer to n less than 1. It's similar to n less than 1, but unlike n greater than 1.
I don't know whether the vortices are Z or Z.
This is known. This is known that yes, they depend on the symmetry class, but in many symmetry classes, when n is some special value, 1 or 2, the classification can be enlarged. That is known. There are many examples of that. Now, another way of saying that I could just not use this replica trick. I can do supersymmetric field theory, and everything I said still carries through. But then this last step, I won't be able to say anything useful because in the supersymmetric symmetry, you have to take basically this is related to Xiaogan's question. In a supersymmetric theory, I have to take twice the number of replicas. So the minimum I can do in my language will be n equal 2. When n equal 2, this is O4 divided by O2 cross O2 that only have Z2 vortices. But that theory is a strongly interacting theory that I cannot solve. But here, by using this fermionic replica alone and taking the limit n go to 0, I can work with basically half of the theory. Okay, in half of the theory, this n can go to 1. And eventually n has to go to 0, which is the challenging part. But now I'm going to basically do an analytic continuation, starting from n equal 1. So, okay, yes? It's a new parameter, exactly. Vortices, yeah. The sign of vortex Fugacity determines whether we go to trivial insulator or topological insulator. But if I have a closed system, it is. So it's in our theory, not in the old theory. Our theory has this. This S naught has the coupling constant T. Yeah. T is the coupling constant stiffness term. Yeah, stiffness. Yeah. And they're here. Yes. Everything I'm talking about is from right now is from the fermionic replica. But if I do the supersymmetric version, yeah, it's replica. But if I do supersymmetric version, there's also this topological, this vortex. There's still this vortex configuration, vortex contribution. Yeah. Yeah.
You said at some point that if n equals 1, then the mod equals Z.
Yeah.
Does that lead to any problem? Because now you're taking
Eventually, we're interested in n go to 0, right? You can even ask, what does it mean when n go to 0? What is topological term? But that's all the wisdom we have so far, right, in the community. Okay, all right. So we treat n as an integer, and at the end of the day, right? Yeah, we take n go to 0. And the interesting thing in this scheme, we can actually do something, starting from n to 1 minus epsilon expansion.
You have the KT RG only at.
But now you will see that for when epsilon is less than 1, I have a new transition that's not KT.
Oh.
Yeah, this is new fixed points. So okay, so yeah, if I look at the coupling constant, how it flows, this is just from the Gaussian theory in 2 dimensions. N equal 1, this term vanishes. Right, the beta function is strictly 0 for a Gaussian model in 2 dimensions. But when n is less than 1, you see this becomes irrelevant. Yeah, become irrelevant. But then the vortex also contributes to the flow of the coupling constant at the order of v squared, and it has to be, because remember the sign of vortex tells you the vortex is a vortex. We use vortex Fugacity, but if it's a closed system, I always have even number of vortices, so it always comes up the order of v squared, and it has to be because plus v and minus v should contribute the same to the partition function in a closed system. And then also there's a RG flow for the vortex Fugacity itself. So then taking these RG equations, there are these 2 new fixed points. Okay, these are not KT fixed points. Okay, these are new fixed points, and they occur at a finite coupling constant T. G basically is inverse T. I'm changing notations, and V is the vortex fugacity, and it leads to this flow diagram like this, and leads into this phase diagram that in this region it all flows to the limit where fugacity goes to 0. This is basically a symplectic metal. In the symplectic metal phase, the vortex fugacity vanishes. We have essentially like an ordered phase. Vortices are penalized. Small t is the ordered phase. Small t. So small t is the ordered phase. So G is, I think, is the inverse of t. So yeah, small g is large t. So you get insulating states. You see the
Both plots, the right upside is while G and T are inverse.
No. In here, no. In here, you see, I think. Let's just talk about t. Yeah, let's talk about t. For small t, because in this theory, when n is slightly less than 1, the fixed point are at small t. Is irrelevant? Yes. Yeah. Correct. I mean, if a t is really small, then you have a metallic phase. But in this theory, there's also a fixed point. That is, when t is very, very small, right? You're right. When t is less than 1/16, it's much less than that. You have metallic phase. Small t means high conductivity. Yeah, I'm sorry for this. So t.
Yeah, the question is, you have these two plots which have the same phases and the same thing. The G and T are inverse to each other. So you have
No, I don't think it's the same. If you look at here, when G is large, it flows to larger G, right?
Yeah,
So larger G is metal in this diagram. I shouldn't really put.
yes.
Oh, that's easy. That's because if you don't have vortex, if you don't have the actually this is an excellent point. Yeah, actually, if you take V equal to 0, right? If I take the vortex fugacity to 0, then this theory is a theory that's obtained in a small t limit, near the order phase. You can think of G being conductance very high, right? Because that's where calculation is controlled, right? And that in that case, the beta function is actually positive, right? In the symplectic class, the beta enhanced, exactly. Enhanced connectivity, yes. Yeah, this line. So maybe it should be T. This probably should be T. I'm sorry. I'm sorry.
Now you have large G, you have insulator.
This should be T. Yes, it should be T.
Okay.
It should be T. It should be T. It should be T. Thank you. Yes. The point is that exactly as when vortex fugacity is 0, T should goes to 0 because we always have a metallic phase. Exactly. Thank you. Okay. Good. Yes. Okay, so these two fixed points are metal insulator transition fixed point, and you see that the key point. I'm running a little bit out of time. Let me very quickly summarize. Okay, the key point I want to emphasize that you get insulating states only when the vortex fugacity is non-zero. Okay, in other words, in the insulating states, the vortex fugacity flows to non-zero values, and that's needed because the sign of the vortex fugacity distinguishes the two insulating phase. If the vortex fugacity is 0, the system must be metallic. Okay, this is a very strong statement. Well, I'm saying that the single parameter scaling theory, where vortex fugacity is taken to be, you can think of it as a special limit where the vortex fugacity is 0. That cannot have a metal insulator transition point because on physical grounds, the vortex fugacity is what makes the system insulating. And the sign of vortex fugacity distinguishes the two insulating phases. If you don't have vortex fugacity, there cannot be insulating states. Okay, so that's O theory. The O theory give you the correct answer in the large G limit because that's control calculation, and then it's sort of extrapolation, right? Extrapolating to this to give you a metal insulator transition fixed point on that line. I'm saying that this cannot be true. Okay, because you really need vortices in this theory to describe. It gives you a metal insulator based on extrapolation. It gives you a metal insulator fixed point.
But it didn't ever talk about
It doesn't talk about that, but I'm saying that theory is incorrect. Yeah, based on physical arguments, okay. This is maybe a too strong statement, but based on this physical argument, that once the system becomes insulating, it's either a topological insulator or a trivial insulator. So there has to be a way of keeping track of them, and it's a sign of vortices that keep track of them. Yeah. So that's basically it. Let me summarize that the topology, the ideas from topological insulators is actually impacting our understanding of topological insulators. Whenever there are distinct topological phases, it implies that there has to be extended states at the phase transition. The phase transition can be in one step through a critical point, or it can involve a metallic region. And within the simplex class, in the nonlinear sigma theory, we identify that the vortex are crucial. The sign of the vortex fugacity determines the topology of the localized phase, either trivial insulator. In the trivial insulator, the vortex fugacity is positive. In the topological insulator, the vortex fugacity is negative. In a closed system, the sign of the vortices doesn't matter. So we have, in terms of the universal critical exponents, the transition from a metallic phase to either a trivial insulator or to a topological insulator, they have the same universal exponents. All properties are the same. And that's actually also supported by numerics. Okay? But the important thing is that in either transition, whether to a trivial insulator or to topological insulator, we have to take contribution of vortices. The vortex proliferation is the only mechanism for localization. It's an essential mechanism. And that's because vortex keeps track of the sign of keeps track of the topology. Okay. So okay, I think that's it. Thank you. Yeah. 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 Right. Yeah. Okay. All right. So let's see. It's here. Yeah. Oh yeah. One thing. Yeah. Maybe one picture if you want to remember. Right. Let me advertise this. Right. So when the vortex fugacity is 0, right, the system is exactly at transition between a topological insulator and the trivial insulator, and the system is forced to be metallic, to be non-localized. Okay. Right. Reminds me of this picture. Yeah. Okay. All right. So okay. Now the question is there such a system that can we you can tune the system to a critical point, but you can also look at the surface of a topological crystalline insulator or a surface of a weak topological insulator. And actually, I should mention these references. Numerically, for example, people studied the surface state of weak topological insulator in the presence of disorder, and they found that even if you make the translation symmetry on average preserved, the system remains metallic. Okay, so that's consistent with what I'm saying based on this vortex theory. And there are many symmetries that can protect this. There are many symmetries that can force the system to be right at the transition point. And one example is this mirror symmetry, right? Reflection symmetry. And the other example is translation symmetry. Translation symmetry on the surface of weak topological insulator, or reflection symmetry in the topological crystalline insulator. Those symmetries enforces the system to be right at the transition point without fine tuning. Okay? And the reason that is true is because, for example, this is a sort of stacking construction I described as stacked planes. And if I dimerize the planes, okay, in opposite ways, the system becomes gapped. But the domain wall contains one helical fermion. So this says that the two domains are topologically different. It's like one domain. You can think one domain as trivial insulator, one domain with topological insulator, right? Although better way to think about it, maybe each one is plus 1/2 and minus half. So they differ by topological index 1. So basically, symmetry enforces if there's this symmetry that's on average present, it enforces the system to be right at the critical point.
Very different argument. Within the signal model
No. Within the sigma model, what this configuration is that it's exactly when the vortex fugacity is 0. You see, the vortex fugacity is tied to whether the system is flowing to a trivial insulator or flowing to a topological insulator.
How do I know that even have
Oh, that's because you always have two different classes, because the topological phase is about gap phases. right? So once I can explicitly gap, once I gap it, once I break the symmetry and gap the system, I can talk about topology. But there are two ways of gapping the surface, and they're topologically distinct. And the argument for that is because at the main wall there's a helical fermion. And then if the symmetry is on average present, that forces in the vortex theory, the forces vortex has to be 0. And that's why I'm also stating that when the vortex fugacity is 0, the system has to be metallic. Okay, both on physical grounds, and this then implies that in the nonlinear sigma model, if I don't have vortex fugacity in the old theory, it cannot give you a true metal insulator fixed point. It cannot be at all. Okay. Yeah. All right. Okay. Thanks.
Because you want to have a discussion right after
Yeah.
The rough picture for the RG diagram is something like this. Like
Yeah.
You did already? Okay. So why don't we start? It's a little easy for quarter of. I'm just a little worried about lunch. So shut that.
Okay. So in the last lecture, we tried to define what is excitation very carefully. The main point is that so do you have some pointer here? This is out of battery. So you can using the trap to define the excitation. So formally, every excitation is labeled by a trap Hamiltonian. So a different trap would define different excitation. That's very natural, have a different wave function. However, we want to define the equivalence of the trap, because if every trap is different excitation, it's not what we expect. We expect some kind of type of excitation. So the equivalence of a trap is defined as you can deform the trap Hamiltonian without closing the energy gap. Then we say these two trap Hamiltonian are equivalent. So this gives us an equivalent class of a trap Hamiltonian. And so then that gives us a notion of a type of a topological order. So this is what we covered last time. And then we can describe how topological excitation can be fused. And how they can be fused. And then different way of fusion give us a different way of splitting the degenerate subspace, which is called the fusion space. And then the connection between the basis of this different splitting is a so-called F symbol. Okay. So certainly this F symbol satisfies certain consistent relation. Very similar to what Michael talked about, that when we try to fuse a four particle like IJKL into one particle P. Okay. So again, there's a different way of fusion give us different way of splitting. Okay. And so all those bases are related by the F matrix. And but then there's two different way of two different fusion paths to go. Okay, so each graph describe a way of a fusion. So each graph represent a particular way we split the degenerate ground states. Okay. So you can see from this graph that represents one way to split them, and this graph represents another way to split the degenerate ground states. However, these two graphs or these two different splitting should be related by a unitary matrix. But this particular unitary matrix can be constructed using the F unitary matrix we just defined, which correspond to relate a different way of splitting, but through some but through some smaller steps. For example, we can consider different way of splitting coming from these two kind of fusion. So here we have a fuse IJ first, then fuse M with K, and etc. Here we fuse IJ first, then KL first, second, then M and Q third. That's all describe different way of fusion. And but however,